Lab 4 bar magnets. Purpose of this lab was to determine the behavior and magnetic moment of a magnetic dipole. Key concepts used were by the Biot-Savart law, magnetic dipoles, and the distance dependence of a dipole. Our main results were that n was negative 2.37 and that our magnetic moment was 3.68. Fundamental principles used in this lab were the Biot-Savart law, which quantifies magnetic fields caused by moving charges, our magnetic dipoles, which are the fundamental field pattern of magnetism and follows 1 over distance cubed, and our dipole distance dependence, where our dipole formula can be linearized, and this can be modeled using linear graphs. Our initial conditions were that our magnet was placed at the end of a meter stick, and that the setup was oriented perpendicular to Earth's magnetic field to later correct B Earth. Our phone magnetometer location was also marked. And for our procedure, our magnetometer was moved until the x component of our magnetic field equaled some value. This distance was recorded for 3 separate trials, and the first 2 steps were repeated for values of these several microteslas. For the off-axis field, our distance was recorded when b equals 100 microteslas. Our magnetometer was moved up by the same distance, and from there our x, y, and z components of b net were recorded, and steps 1 through 3 were repeated for 3 trials. So this is our data for parts 1 and 2. For part 1, we graphed our data, resulting in an r-squared value of 0.991, which indicates a strong linear correlation. For our analysis, we can use our linear model to compare our slope to the linearized magnetic dipole formula, and from there we can determine mu, where ln k equals negative 0.3057, and from there we can determine our mu of 3.68. And from the spreadsheet functions, we can determine that our average B net was 80.07 microteslas. For our computational model, we can start off by defining constants, creating a magnet at the origin, and also creating our magnetic dipole field function. And we can input our measured values of distance for the off-axis field, and we can also create a representation for the off-axis field using an arrow. And this is what our code results us, where our cyan and orange arrows are the on-axis and perpendicular observation locations, and our magenta arrow is our off-axis field. Our code also results that RB magnitude at 45 degrees equaled 4.187 times 10 to the negative 5th teslas. For our results, we determined that our magnetic dipole moment equals 3.68. Our distance dependence was observed to be negative 2.3672, which was lower than our expected of negative 3. Our off-axis field was actually predicted to be half as big as what was measured at 8.01 times 10 to the negative 5th teslas. The assumptions we made were that the dipole approximation of a bar magnet held true, our uniform ideal magnetic moment mu also existed, and that there were no external fields or noise. Some potential error sources were misalignment resulting in wrong correction of B Earth, imperfect readings from the magnetometer, inaccurate sensor location on your phone, and or the bar magnet not being a point dipole. If we hadn't oriented our experiment to be properly oriented, this would result in B Earth interfering with our X and Y component readings and making our results inaccurate. If we were to stick 2 identical magnets together and repeat the experiment, this would effectively result in a magnet with double the dipole moment, and this would result in larger measurements, but overall our directions would remain the same. So our main outcome was that measured magnetic fields follow the dipole pattern, but our values were higher than expected or calculated. Our measured off-axis field was actually larger than our calculated magnetic field, and our n value was lower than expected. And these discrepancies likely come from experimental error and using the dipole approximation. Thank you for listening.